Good morning, class. Welcome to Quarantine Logic Week 2. Today, we're going to talk about physics. Now, what is physics? Physics is the study of matter and its motion and the causes of this motion. So it ultimately asks the question, why do things move? Right? And the answer is because of forces. Is the ultimate answer. And so physics studies the relationship between all these fundamental forces of nature. So Aristotle is one of the first people to really answer these questions. And he says that there's two kinds of motion. There is natural motion and motion by force. Now, it's important to understand the difference between the two, and I'm just going to make a little example. So Aristotle notices that some types of motion happens on its own. For instance, the sun and the stars rotate around the earth every day. This is a natural motion, and nobody's pushing the stars or pulling the stars necessarily. It happens naturally, right? Now, there's all sorts of kinds of motion by force. For example, a motion by force would be someone is moving something with a push or a pull. So for example, let's say I'm building a house and I pick up a brick and I move it somewhere else. This is motion by force. Okay? Now Aristotle says that the natural motion is based on the four elements. So depending on what kind of element you are, it's going to affect what sort of motion you're going to have. So remember the four elements. You have earth, water, air, and fire. Okay? And he says that each of these four elements has its own natural place. So he says the natural place of earth, which I'll color in green, is the center of the universe. So that's where earth naturally wants to go. It is going to fall towards the center of the earth. Then the natural place of water is just outside of that. So water is on top of the earth, right? When it rains, the water is falling from up in the sky towards down on the earth, because water has this natural place on top of the earth. Then after that you have air. Outside of that, our atmosphere, it's up and around where you breathe and all this. And then way up out here you have the ring of fire. And essentially he's saying that the stars and the planets and the sun is made of fire. And so whenever you light a fire here on Earth, that fire wants to escape to its natural place, and so it's going to rise towards the sky, towards where fire naturally goes. And so he says all natural motion is based on these four elements returning to their natural place. Now, a very important idea of his is that he explains like what happens when you drop or throw a rock. Okay, now his explanation of dropping a rock is pretty solid, but his explanation of throwing a rock doesn't make a lot of sense. And so later on, the main person we're going to talk about today is going to call that explanation into question. But let's explain what happens when he says you drop a rock. So we'll have our little guy. Here's Aristotle. It's a very lifelike picture of him. And he's holding out a rock. Give him another arm. He can have 2 arms. And he drops the rock. And he says, here's what happened. Whenever I let go of the rock is returning to its natural place, which is towards the earth. It's made of earth, so that's where it belongs. It's on the earth, right? So he says that's what's happening, okay? But his explanation of throwing rocks is a little different, so, because here's the problem with this theory. His idea is as soon as you let go, as soon as you stop moving it by force, it's going to return to its natural place, right? Well, let me show you what happens if you throw a rock. It follows a path like this. So let's say he throws it now. It goes something like this, right? This little arc, this parabola, is the pathway something takes when you throw it, right? Or if you kick something or whatever. So if you've seen football, for example, you've probably seen this path all the time. Every time the players throw passes or kick off or punt or any of that thing. Also basketball, this is sort of the pathway the basketball takes when you shoot it. So this sort of arc, this parabola. And Aristotle has to explain why it takes this path. Because even back then, people knew that's the path that it takes. You could throw a rock. Throwing a rock, we assume, followed the same physics in Aristotle's time as it did now. And so it made this pathway. And so his explanation is this. Whenever you throw the rock, it's going to push you're going to push the air also. So you push the rock forward, but you also push the air forward. So as the rock is traveling, the reason it doesn't just fall down is because this air that you pushed, the air is pushing the rock along the path. Because otherwise, think about it, if his idea is that as soon as you stop applying a force, it's going to return to its natural place, then why does the rock travel upwards and outwards when it should just be falling straight down, even though you threw it? Does that make sense? He's saying somehow the rock continues to move after you threw it, right? When the rock's right here on the path, are you still pushing it? No. So why does it keep traveling forward then? Well, he says the air is what's pushing it forward. And we'll talk about why that is a little suspicious. So, enter John Philoponus. So John Philoponus lived in the Greek East after the split of the Roman Empire. So he lived in the Byzantine Empire, largely during the reign of Justinian. And the reason I noted that is for one thing to explain when he lived, which is around the 500s, but also to show that it makes sense that the greatest scientist that ever came out of the Greek East probably lived during this time where there was a lot of prosperity in the Greek East. And he is noted for his theory of impetus, which he introduced while writing a commentary on Aristotle's physics. So Aristotle writes this book called Aristotle's Physics, and John Philoponus, he writes a commentary about it. Commentaries on great literature greatly drive knowledge forward. Okay? We read great books. That's part of what we do in the classical tradition is we read the great books. And John Philoponus was a very classical thinker, and so he's reading the greatest books of science. For example, Aristotle's Physics. That was the best physics book that had ever been written for a very long time. It remained the greatest book. And what we want to do is highlight the great ideas that are contained within them and explore them even further and offer our own insightful questions and so forth. So that's what John Philoponus did. He would read some of the things that Aristotle wrote, and he would write down his own insightful questions. He would explore some of the ideas. He would even disagree with certain parts, as we'll see in a few minutes, and offer a better explanation with maybe more observations and reasoning. And he explained very thoroughly why it doesn't make sense what Aristotle said in this spot, or why it maybe makes sense, but there's actually a better explanation. Okay. Now this idea of writing a commentary is really important. So there's also this guy. This is later on, but it's an interesting story that I think answers why we should do commentaries and think about commentaries. This guy Fermat. Okay. This guy his name was Pierre de Fermat, and he was a mathematician. And he was reading this work by this guy Diophantus, who is one of the greatest mathematicians ever. And he's reading this work called The Arithmetic by Diophantus, and Fermat is actually coming up with his own theories in the margins, and he's writing down these just great notes. And his copy of The Arithmetic ended up sparking all this amazing stuff. And there's just so much more that could be said about this, but I really just want to highlight that this is an important part of the classical intellectual tradition. In fact, in medieval universities, which we're going to get to that very soon, the first universities are going to come about within the next few hundred years of our history that we're going through. And this is something that you had to do. I think it was whenever you were in your sophomore year, so to speak, whenever you're in your second year of college, you would have to choose one of the great books and write a commentary about it. Whether it be a book of scripture or something like Aristotle's Physics or whatever it was that you chose, you had to choose from one of the great books, and you copied it, you translated it, you wrote down the book yourself, and you would also have to write your own commentary. The next essay we're going to write actually in this class is going to be a commentary. Anyway, let's get back to the story. So what is this theory of impetus that he is so famous for? Well, first of all, he realizes that the air cannot be what moves the rock. And he uses both reasoning and observation to show this. So he says, listen, if I go up to a rock and I blow on it with all my might, I will not move that rock 10 feet, right? He says, if I run up to a rock and I wave my hand as hard as I can to try to waft some air towards it, I'm not going to move that rock, right? So he says it can't be that you throw the rock and then the air pushes it forward. He says the air pushing it forward, if this at all impacts where the rock goes, if it does at all, it has such a small, tiny, insignificant impact on the movement of the rock. So he says, but clearly the rock is resisting its natural motion for a while, right? If I throw a rock up, it actually does go up, doesn't it? It goes up. It goes higher than me. I could throw a rock maybe 10 feet in the air, 20, depending on how heavy the rock is, right? So it's able to not just fall straight down, it's able to go up. And he says that that is because the person imparts an impetus or a tendency to move into the rock. Now think about how abstract this is, what he's saying. He's saying that whenever you move the rock, you are giving it this tendency to move in the direction that you threw it in. It's almost like you're changing its natural motion, just temporarily. You don't give it enough impetus to travel upwards forever, right? You don't throw a rock hard enough to where it just travels upward forever. But what it can do is you can give it enough impetus maybe to travel 30 feet, and then it's going to fall back down, right? Because you only give it so much impetus. More force is going to be more of this impetus for motion that you give it. Okay, and so this is so much closer to the real physics of what's happening, is that you're actually imparting a tendency to move directly into the rock. Okay, because it's like the rock has this inner capacity for motion that you are sort of enhancing that when you throw the rock. It's very abstract. Okay, you can't see this inner force and tendency, but it's there. Okay, and this is if any of you have studied Newton's three laws of motion. So why is this important? Because this is so much like Newton's first law of motion. Isaac Newton was also a classical thinker. And one of the people that he was reading when he came up with his laws of motion, which revolutionized science, was John Philoponus. He was reading his commentary on Aristotle's physics. Why was he reading this, by the way? Well, because some other classical thinker between Philoponus and Newton had cited Philoponus in their work. Okay, which is amazing. So Newton was reading this book and he didn't understand it because he was mostly teaching himself physics and math. He didn't really have a teacher in this way. So he's reading this book and he doesn't understand it. Well, he notices this book keeps citing this guy, John Philoponus. So he says, man, I need to read John Philoponus. So he keeps citing him. He keeps having all these quotations from his book. I just need to read John's book, the commentary on Aristotle's physics. So what is the impact that Philoponus had on Newton's laws? Well, the theory of impetus is what leads directly to Newton's first law of motion. So Newton's first law says that an object in motion has a tendency, or an inertia is what he uses. I'm not exactly sure of the Latin word that he uses here, but it actually comes from the Greek word for impetus, right? Because he's directly borrowing the idea from Philoponus. But he brings the idea further to say that all objects have this tendency to stay in motion if they're moving, and they have the tendency to stay at rest if they're resting, unless acted upon by a force. So this completely overturns all of Aristotle's ideas at this point. We realize that there is no natural motion, that only forces can cause changes in motion. So if something is falling, it's going to keep falling until something stops it from falling. If something's running, it's going to keep running until something stops it from running. Or rolling is a better explanation than running. Right? And so this is all the result of this long period of time that passes from Aristotle to John Philoponus, and then from John Philoponus to Isaac Newton. Now, why did it take so long from Philoponus to Newton, right? How come it took so long for us to realize that Aristotle was wrong about natural motion? Well, for one thing, because when you drop a rock, it does seem to naturally move by itself. That's what Aristotle said, is that it moves by itself. What's pulling it? What's pushing it? I don't see anything pushing or pulling the rock when I drop it. It must move by itself, right? In fact, why does the moon orbit the Earth, go around the Earth every night? Is that, what causes this? It seems to be happening by itself. I don't see anyone pushing the moon or pulling it. And says You might say, well, of course, it should be obvious that the Earth is what's pulling down the rock. It's this invisible force of gravity. And I say ridiculous. That's not obvious. There's actually no evidence of that. There's no evidence that the Earth is somehow pulling the rock down. At least there is no evidence of that on Earth. Okay, and so this is going to be continued later after we cover 1,000 more years of history. The question is, how did this invisible force of gravity get discovered in the first place? Well, when we get to Isaac Newton, we'll learn more about that. Okay, everyone, have a great rest of the week. Remember to answer your quiz questions by Thursday at 5 o'clock. The quiz will be posted this afternoon. Also, you need to read Chapter 8 from the book, from the red book, The Beginnings of Western Science, okay? And maybe you want to read the quiz questions before you read the chapter so that you know what sort of things to be thinking about as you read. I'll see you guys on Tuesday, God willing.